for your name?
De Ken.
Is this right?
I don't know how do you. How
Okay. So this is a Chinese pinyin. So
yeah, I'm not. Yeah, okay,
So
fine.
this is Benjamin
Ah,
De Ken.
okay, it's Benjamin
Benjamin
De Ken. So
De
I think
Ken.
De Ken is fine.
De Ken.
Yeah, De Ken is fine, but Benjamin.
Okay.
But if you
Benjamin.
mispronounce it, that's fine. Don't
Okay,
worry.
so, okay.
You can try, but
Okay. Benjamin
Benjamin De Ken.
De Ken.
Yes,
De Ken.
De
De
Ken.
Ken or De Ken. De Ken.
De Ken. Yeah.
De Ken. Benjamin De Ken. Okay. Let me try.
Yeah, all right. But if you mispronounce it, that's fine. Don't worry. I know that I have a lot of trouble with my name, so even between French people, so that's sometimes they change my name and put an S, change the E into U. Well, so so don't worry.
Yeah, good. Okay, so let's begin. So the third speaker is Benjamin Ducana. Yeah, thank you.
Pretty good.
Yeah, so the title is Resolving Subcategories for Gentle Trees. So please.
Thank you very much. Hello, everyone. Thanks for coming for this talk. And it's a pleasure to be in this conference. Wonderful conference. I hope you enjoy it. So today I will talk about a big work, joint work with Michael Schwiner. There are already 3 papers on this thing. And we are talking about resolving subcategories for gentle trees. For some of you who want to have the notes with you, you can scan the QR code. I hope it doesn't bring back bad memories for you, but well, if you prefer to go to the website, that's also fine. So, some motivations. What about resolving subcategories? So, the first idea is to generalize the projective modules. The idea of resolving, as it is its name, is to be able to approximate any module thanks to a resolution using this kind of category. So there are different studies done in the past. So Osander-Wrighton and we have also Adachi and Tsukamoto who work with the link between resolving subcategories and hereditary co-torsion pairs and also tilting objects. And on the other side, we have also Ringel work with construction of triangulated categories via by-resolving subcategories. So here we are calling for categories such as we have a resolution, but also a co-resolution with these categories. And by doing some quotients, we are able to find out those categories. So today, my main goal is to give you an overview of the whole work and give you some hints and even some big results among all of this. All right. So as usual, when we work with quiver representations, we have some settings. So here, K will be an algebraically closed field. Q are a gentle quiver, and we will focus on gentle trees. Just the graph is a tree. And some let's say, basic things. Representations of the quivers correspond to looking at modules over the past algebra and precisely the quotient here with relations we want to put on the quiver. Projective elements, indecomposable elements, and something which is pretty much important here, I consider subcategories that are closed under sums and summands. They are full, so they are completely described by the indecomposable representations in it. So, resolving subcategories, I have to give the definition. Here is a definition, because there is a generalized definition that exists for a generalized setting, but here, as we are working with representation of quivers, we can simplify a little bit. So here, a resolving subcategory will be a category such that you have the projective elements in it, you have your category which is closed to under higher extensions, and this is also closed under kernel of epimorphism. You can still simplify more by saying that they are just closed under extension, the simple extension x1, and also closed under CZGs. We can really simplify this definition. I think this is one of the remarks which will follow. So I take this gentle quiver, really kind, and here there's on the right-hand quiver, so all the indecomposable elements are represented, and also all the morphisms, irreducible morphisms, are the black arrows, and for the blue arrows, this is the usual AR translation. And on the other side, you have the poset, which is a lattice, the poset of resolving subcategories. So let me explain the notations, because I could just describe what are the indecomposable elements in it, but I've done pretty much something more precise, saying that I take a subset that generalizes the resolving subcategory, and not any subset. We will see that later. But well, for instance, if I want to see the resolving subcategories associated to the empty set, this means that this is the smallest resolving subcategory, and the smallest one is given by the projective elements. And as the projective elements are always in the subcategory, I don't need to say that they are here. All right, for another example, if I look at the resolving subcategory generated by 2, you see that you have the extension between 2 and this projective element, and you have to take the indecomposable elements that are appearing as extension. And that's it. This will give you the resolving subcategory generated by 2. And in some sense, you can see also in this poset that 2 is bigger than 2,4 and 2,3 in some sense. So the sense is just the resolving subcategory generated by 2 is bigger than it is bigger than the one generated by 2,4 or 2,3.
So the maximum element can be also written just 2, right?
Yes. Yes, exactly. Yeah. That's the idea. Yeah, that's the idea. Let me show you another example. Here, the 2 elements are not really comparable in terms of resolving subcategories. So to describe this one, I can take the 2 elements here, and then I complete with extensions. So here we don't have really extensions, but we have a CZG appearing, which is a kernel of epimorphism, once again, and we have 2, 3 appearing. All right. So here are some facts. Any resolving subcategories can be described thanks to the non-projective indecomposable elements. What I said just before, we can simplify more the definition by focusing on X1 and CZGs. There is an algorithm already existing given by Takahashi, which allows us to compute the resolving closure, which is the smallest resolving subcategory generated by some collection of indecomposable elements. And here we will focus more in the computation just by computing things around indecomposable representation, which is quite different of the algorithm given by Takahashi. And the poset is a lattice. We have a conjecture that's saying this is trim, but yeah, this is still a conjecture for the moment. All right. So let's go back to this example. So we don't really see distinguish the colors, I think, but you should have some elements that are red. Those elements are joint irreducible elements in the poset. So as you can see, the joint irreducible elements are precisely what we call the monogeneous resolving subcategories that are the ones generated by exactly one indecomposable non-projective element. And so you can really focus on this kind of order and try to describe the other categories thanks to those elements. All right. Here is another example just to show what could happen if you don't have a tree. So here this is again the also on the right-hand quiver. I just have done a universal cover of the also on the right-hand quiver in some sense. That's why I have a copy of one appearing, but that's fine. Here is once again the resolving lattice, we could say. But you can see that this time for the monogeneous resolving subcategories, there is one that is not joint irreducible. And another thing, if you count all the elements that are not projective, if you have good eyes, you can see that someone is missing, 2, 3. But 2, 3 is the same as 1. If you take the resolving subcategories generated by 2, 3, you get 1 by taking this kernel. And from 1, you can get 2 free, once again, thanks to this comma. So there are few complicating things that are appearing if you not focus on trees. Okay, so here is the result. So if we focus now on gentle trees, yes, the monogeneous resolving subcategories correspond exactly to the joint irreducible elements of the lattice. And we have a complete bijection. We can generalize a little bit this result to directed algebra, which means that the also on the right-hand quiver is acyclic. And yeah, if you go through the proof, this is the main ingredient of the proof. Another thing I want just to mention, in a big group, and I think this is in progress, we are giving a large family of joint irreducible elements for any gentle quiver. If you are interested, I can probably give you some description about that. Let me just motivate why it is interesting to see the joint irreducible elements. Here is another lattice. Another lattice. And in red, you can see what are the joint irreducible elements. How can you describe F thanks to the joint irreducible elements? You have different possibilities. You can tell me that this is the joint of D and E, the joint of D and B, D and C. But the one which will be really interesting is the one given by D, E, and C. They are the greatest joint irreducible I can have as kind of ideal in the subposet given by the joint irreducible elements. And this will be the kind of decomposition we will look at. So you can always describe elements from your lattice thanks to those joint irreducible elements, and this anti-chain, which will be unique under those two things. First of all, of course, you want to have your element as a joint of the elements of your anti-chain, but also you want to have the greatest elements under this relation, which means that you are looking at the ideal order generated by those anti-chains. All right. No question for the moment? Fine. Okay, don't hesitate if so. All right, so now the first step will be to describe what are all the monogeneous resolving subcategories. To do so, we will use the geometric model and we will slightly modify it. So there are lots of people who are interested into and give introduction into this geometric model. The idea is to have a dissection, a green dissection. So we have a surface here. This is just a disk with marked points on the boundary, and you have alternated colors in it. And the green arc corresponds to vertices of the quiver. And each time you have an angle, this corresponds to an arrow in the quiver. And you have also relations. Each time you have, let's say, roughly 2 arrows that are in the same cell of your dissection. All right. See that the orientation is maybe not usual. We are using not the counterclockwise, but the clockwise orientation. This is for the purpose of computation things. All right, so I choose an indecomposable element, which corresponds to a string, so a walk, an admissible walk, I should say, radius walk in your graph. And this corresponds to an accordion of the graph. So I will just go, just skip the definition, but if needed, I can go through it. And so, as I said, we will slightly modify the model. So the idea is to focus on the projective element, because the only interaction we could have between indecomposable elements and the accordions may be already there to build a resolving subcategory is the one that are projective. So we take the projective elements. You can see that this is mainly a shift of your dissection. And from there, we will focus on the ones that are interacting with the accordion. So the ones that are interacting, we can define them either combinatorially by saying that you have some crossings, you have some big cells at the beginning and the end, etc., etc. But we can also define them in algebraic terms, saying that we have extensions, there are projectives appearing in the projective resolution of your indecomposable element, etc. So those are called the neighboring projective accordions. And without going through too much details, we give an explicit computation, thanks to some colorations we put on the vertices, that allows us to compute the whole resolving subcategory generated by delta using those things. So you can see that there are some accordions between green and orange points, etc. But this is really too technical here for the moment. But we have an explicit way to compute them. Okay. And so now we have the joint irreducible elements. We can now try to compute any resolving subcategory. And to do so, we need to understand the interaction between the different accordions we want to have in our resolving subcategories. And so we have those moves appearing, and those moves just encode the behavior between the accordions. So this one, KE move, just encodes the kernel or kernel of epimorphisms or extensions. Here, more precisely, arrow extensions. V move can be seen as higher extension things between the accordions. And we have also different other moves. Here, it's more about the overlap extension. You have two accordions that are crossing, and you can get the two other indecomposable elements. So yeah, the main idea is really to keep the interaction between the different accordions. And there are also few moves. I think I didn't draw them, but there are also few moves to also encode the interaction with CZGs. Because this is not enough, unfortunately, to know the interaction between the main accordions we want in our resolving subcategories. Sometimes we need to go through some CZGs elements. All right. And the main point is to determine the anti-chain, the one I showed you before. So to do so, we go through this algorithm. We take a collection of indecomposable elements. We extract a maximal anti-chain from this collection first, and then we compute those moves. Those moves, again, extensions, kernel of epimorphism, etc., etc. And we keep at each step the relevant one, because what could happen is we will make appear some other accordions that can be greater than one or two of the previous accordions we had in the anti-chain, the previous anti-chain. So we have to do some comparison things, which could be done again using only the geometric model. And then, if we have new elements, we continue. Once we don't add anything else, we get exactly the anti-chain we want. And so here I'm pretty messy in the notation, but the idea is to say that if you want to compute the resolving subcategory, take your collection of accordion, compute the monogeneous resolving subcategories, so just the indecomposable elements, take the union, and take then the additive category if you want to see it as a category. This is the idea. All right. Let me end with this last result, which is about the last paper we put on archive just before the conference. So we are able to realize combinatorially the correspondence, also on the right-hand correspondence, between resolving subcategories and tilting objects in this case. So this is kind of a translation. So there is a more precise statement we could do for any functorial finitely, functorial finite, something like that. I don't remember how to state it. But well, there are some generalization we can do on this statement, and we just apply it for our case. And the idea is to, from the anti-chain we got that described the resolving subcategory, we have to rigidify a little bit, because what could happen, I can go back to one, yeah, this one. For instance, this anti-chain is not rigid. You have this short exact sequence that tell you that you have an extension between 2 and 1. So you have to rigidify, saying that you will delete some elements, and not you will not do things just. You will be, of course, be careful. You will be careful on what could happen between the indecomposable elements. But well, here we will just delete 2. We will get this rigidified element, and then we will compute what we call the Bongard complement of this collection. And there is a beautiful combinatorial way. Oops, sorry, I go too far. A really combinatorial way to complete this, to compute this, by taking the projectives that are orthogonal to the elements we have, and then some completion still to be made. But this can be really really smooth. All right, so let me end this talk with a quick call of what we have done, and also further directions. The first one is to study the lattice of resolving subcategories for gentle quivers and even more, maybe string quivers, maybe skew gentle, depends on what we can do. Because as you saw, this is really focusing on the geometric model and modified it. So it could be nice to have a geometric model, obviously. But well, so this then extend the computation procedure in those settings. Of course, there are some unavoidable assumptions as finite global dimension or functorially finite categories, things like that, that could change the computation into a messy thing. And another thing could be to play with exact structures and maybe focus on resolving subcategories depending on some exact structures. That could be also another direction we could go through. Well, I think I can end here. So thank you very much.
So in the representation finite case, do you have any algorithmic way of computing this lattice of resolving subcategories? So say I give you code to your computer and give me the lattice.
So let's say by hand for the moment. So the idea is to focus on the indecomposable element, and you will order the indecomposable elements depending of the resolving subcategories they will generate. So just inclusion things. And following this, then you will try to understand the interaction between those elements just by focusing on the anti-chain you want to use to generate your resolving subcategories. Then, the difficult part is really to encode what happened in terms of accordions if you want to do it with the geometric model. Which we have tried to compute a little bit with a computer, but still messy because, we have really to understand how to encode different crossings and things like that. Even it is in a disk, seems like pretty messy. Even for if you just look at once again the moves. So you have to focus on the crossings. Some of the things are pretty easy, but for instance, this one is less easy, and also some of the moves I didn't show about CZGs. That could be a bit messy, but we have that.
Maybe it's a bit naive, but you mentioned this conjecture on the structure of the lattice of subcategories.
Yes.
Do you have examples, maybe when, I don't know, for simple enough trees, when you have further structure of this lattice? Maybe.
What do you mean by further structures?
I don't know, maybe it's naive, but again, if it's distributive or something like that.
At least what I can say is that we compute a lot of examples, and we start to have to try to use some tools from trim lattices like the Galois graph, if you heard about that. This is a graph that link joint irreducible elements and different things linked to some kappa map. What could be a kappa map is just taking the the perp of your resolving subcategory, xperp of your resolving subcategories, and some co-resolving things. But well, there is some computations that really tells us a lot about this should be a trim lattice. At least for trees, we have a big hope that we will have the proof. For more general case, this seems to be difficult because as you saw already in this example, there are some identifications that could happen, some resolving subcategories, monogeneous resolving subcategories that are no longer generally irreducible. So seems like not that good to handle it, but yeah, yeah, we have some hope from just by using tools from trim lattices, and I think yeah, let's say we have some ideas of the proof, but seems not fit things together as good as we want for the moment.
So, do you already have some result with changing the exact structure, or just
no
direction? Or?
Let's say we have some ideas like some of the crossings will no longer be interesting, or some of the triangles will no longer be interesting. So you could continue to compute those moves, but some of them will use or not the exact structure. And if you don't use it, then the computation you can forget it. So we have some ideas, but we didn't go further yet.
Okay, then please thank the speaker again.
Thank you very much.